carboxymuconate 6-phenylaldehyde. And keep in mind that in all these videos that we're doing on the catabolic pathways, we're going to make the assumption that we're in the fasting state. We have low blood glucose. We're going to have glucagon as the prevalent pancreatic hormone. And in other videos, we'll make other cases for maybe what happens when we have insulin present after a high carbohydrate meal. See you in the next video. Welcome back to tryptophan catabolism. In the last video, we looked at the pathway of tryptophan conversion to 2-amino-3-carboxymuconate 6-phenylaldehyde. In this video, we're going to look at the degradation of that molecule, which is shown right here, all the way down to glutaryl S-CoA. And then in the video after this one, we'll look at the conversion of glutaryl S-CoA down to acetyl-CoA. So ultimately, let's go back and review what we've seen up to this point. Okay? When we used chinureninase from the last pathway, we generated alanine, and we saw that that alanine could be converted into pyruvate, and then that could ultimately be converted into glucose. So what this means is that this particular part of the pathway, at least the part that we generated alanine in, is glucogenic. The reason it's glucogenic is because we can use the pyruvate to form glucose. Okay? So that's glucogenic. What we're going to find about the last part of this pathway, in which we're going to produce acetyl-CoA, is that it's ketogenic. And the reason it's ketogenic is because we're going to produce acetyl-CoA, and that's going to be used in times of fasting to produce ketone bodies. And the ketone bodies can be used by the muscle, they can be used by the brain, and so forth, much like glucose can. Okay, so this reaction is 2-amino-3-carboxymuconate. Right. It has your cysteine sialate nucleophile on the active site. It has your Bronsted-Lowry base acid proton donor acceptor in the active site. And so it's going to be your typical aldehyde dehydrogenase. If you need to see the mechanism on that, I recommend that you go watch it. We have the video in this playlist. It might be around here somewhere. But the whole point is we're going to generate NADH, and we're also going to generate 2-amino-muconate. Okay? Now, the NADH, it's not like we're going to get a net NADH, because we're actually going to consume it in the next reaction, so it cancels out. Okay? So 2-amino-muconate is going to react with an enzyme not yet characterized. That's what this ENYC means. It means enzyme not yet characterized. And so if you go to a database and try to look for this enzyme, you won't find it. It has no EC number yet. They haven't isolated it, but we know what the reaction is. It's basically going to consume the NADH that we just produced, basically, and it's going to use water to deaminate 2-amino-muconate. And when it does that, it generates this special molecule right here, which is called alpha-ketoadipate, or sometimes you'll refer to as 2-ketoadipate or 2-octoadipate. And alpha-ketoadipate is going to get consumed by a member of the alpha-keto acid dehydrogenase complexes. And this particular one is called alpha-ketoadipate dehydrogenase complex. Why is this significant? Well, mechanistically, it's identical to the other alpha-keto acid dehydrogenase complexes that we've seen. Well, what are those? Well, that's the pyruvate dehydrogenase complex, the alpha-keto-glutarate dehydrogenase complex, and the branched-chain alpha-keto acid dehydrogenase complex. So all of those things are mechanistically identical to this one. And if you think back to our study of the pyruvate dehydrogenase complex, you would realize that the first enzyme is our decarboxylase. So this is enzyme 1, and it would be our alpha-ketoadipate dehydrogenase, or alpha-ketoadipate decarboxylase. And then we have enzyme 2, which is going to be dihydrolipoyl transacetylase. And in the process, what we're going to get is this glutaryl S-CoA. And in the next video, we'll actually look at glutaryl S-CoA catabolism. And then, of course, we have enzyme 3, which is our dehydrogenase, or dihydrolipoyl dehydrogenase. And this is going to use FAD and NAD to regenerate the resting state of the enzyme. And we're going to get NADH out of this. And, of course, the NADH is going to be used by the liver cell that's doing this in order to fuel NADH through the oxidoreductase or complex form of the mitochondria. So we get the NADH out of this, and that's used to power the pumping of protons by the mitochondrial respiratory chain for the synthesis of ATP. And the glutaryl S-CoA that we generate is going to go into glutaryl S-CoA catabolism, which we will see in the next video. Okay? So I hope this video gave you a little bit of intuition of how we take the destroyed aromatic ring, which is 2-amino-3-carboxymuconate 6-phenylaldehyde, and convert it all the way down to alpha-ketoadipate, and then ultimately to glutaryl S-CoA. See you in the next video where we actually go into the catabolism of glutaryl S-CoA. In this video, what we're going to do is we're going to go over lysine catabolism, and this is specifically the lysine catabolic pathway that's observed in mammals. And what we're going to see is this is actually going to converge with tryptophan catabolism. In tryptophan catabolism, we generated something called alpha-ketoadipate, and then we saw the catabolism of that molecule. Well, lysine catabolism is going to converge with tryptophan catabolism by producing alpha-ketoadipate. We won't show the conversion of alpha-ketoadipate to acetyl-CoA, but suffice it to say, I'll say right now that because we're producing alpha-ketoadipate, this is going to be a ketogenic amino acid, and that's very important because this is one of the amino acids, one of the 2 amino acids along with leucine, that's only ketogenic. Every other amino acid besides leucine is going to be glucogenic or glucogenic and ketogenic. And this is going to be one of the only ones that's going to be truly ketogenic. Okay. So let's kick it off with the enzyme lysine alpha-ketoglutarate reductase. Now what I want to say is this lysine alpha-ketoglutarate reductase is part of a larger mitochondrial enzyme complex. And specifically, it's a complex between this enzyme and another one called saccharine dehydrogenase. Specifically, the way the enzyme is set up is where lysine alpha-ketoglutarate reductase is near the N-terminus, and this C-terminus contains saccharine dehydrogenase. So it's a bifunctional enzyme complex. Okay? But right now, we're only going to concern ourselves with lysine alpha-ketoglutarate reductase. Now, this is a strange catabolic pathway because we're going to actually have to waste in NADPH. So here's our NADPH. Ordinarily, when we think of wasting in NADPH, we think of biosynthesis. That's ordinarily the reason we require NADPH. But in fact, this is one of the few catabolic pathways where we're actually going to have to consume one of them. And what this enzyme is going to do is it's going to condense lysine and alpha-ketoglutarate with the subsequent loss of water. In other words, if we were looking at this molecule, the oxygen that's part of water is the one I'm going to highlight purple. It's the ketone oxygen of alpha-ketoglutarate. That oxygen ends up in this water molecule that gets lost. And so what lysine alpha-ketoglutarate reductase does is it condenses lysine and alpha-ketoglutarate into a molecule called saccharine. And oftentimes, what this pathway is called it's called the saccharine degradation pathway. Much like in tryptophan catabolism, we have the kynurenine pathway. This one's called the saccharine pathway. And the reason it's called the saccharine pathway is because now once you form saccharine, you're committed to the catabolic pathway. This is the point of no return. Okay, so saccharine is going to be consumed by the C-terminal side of this bifunctional enzyme called saccharine dehydrogenase. And this one's not going to be an NADP-dependent enzyme. It's going to be an NAD-dependent enzyme. And specifically what it's going to do is it's going to dehydrogenate and cleave off L-glutamate. Okay, so when we dehydrogenate, we're going to get out NADH, and we know what happens to NADH. That's going to get consumed by NADH-ubiquitin oxidoreductase, which is complex one of the mitochondria, and you get the pumping of 4 protons from the matrix into the inner membrane space, right? And that powers ATP synthase. Well, when we cleave off glutamate, that leaves this molecule called alpha-aminoadipase 6-semialdehyde. And the reason I say 6-semialdehyde is because the 6th position is what has the aldehyde. And you can probably imagine what's going to happen now. We're going to dehydrogenate it, right? We're going to dehydrogenate it. And specifically, we're dehydrogenating the aldehyde, right? And you can imagine that if we dehydrogenate an aldehyde, it's going to end up as a carboxylate. And it will, and if you notice, in alpha-aminoadipase it is. And the enzyme that catalyzes this reaction is called alpha-aminoadipase 6-semialdehyde dehydrogenase. Now, this is a strange aldehyde dehydrogenase for several reasons. Number one, it's expressed in multiple compartments within the cell. It's expressed not only in the mitochondria, it's also expressed in the cytosol and the nucleus. And that's bizarre, because in our bifunctional enzyme of lysine ketoglutarate reductase and saccharine dehydrogenase, this is